All right, y'all, let's get started. Sorry for the delay here. Please, let's get started. Hope everyone's having a good week and enjoying wearing not a jacket. All right, so we're playing catch up still, but we should be able to finish off lecture 5 and 6 today. So kind of all over the place, but just as I did every other time, I took the slides from lecture 5 and I just put them in this PDF that I had posted. So you can just view it on there. And in the top left, you'll see those slides that are associated with lecture 5. So we're going to do recap on that and then get into another lecture on soil composition. Before we get started, please remember for the lab report for moisture content, that is going to be due on Friday at midnight. So regardless if you're in Wednesday or Thursday, it's going to be due on Friday at midnight. And also, please remember, you need to get your moisture contents or get your dry weights from the lab. Has anybody not done that yet? Is that all the groups gotten in there, coordinated with Joseph? Okay. If you haven't, please, I can unlock it afterwards, because you also need to share and post your data to that Google Sheet, because all the lab groups are posting and presenting all the data. And the goal of that is to see the variability in moisture contents with potential sources of error, whether it's collecting it or whatever time, season, that thing, and then also with depth. So you're going to plot and the variation with depth. So please make sure to do that. Do not just post your specific group's data. Aside from that, we will have lab this week. So tomorrow and on Thursday, the lab section, we will have, we found out yesterday that a major piece of equipment in the lab is broken, so the vacuum doesn't work. So we may have to put some asterisks on the lab report, or we'll magically get it fixed by tomorrow. So just giving you a heads up for that. But regardless, we're still going to have lab, and it's all going to be inside, but you're going to be working with water and soil, so just keep that in mind. But we are not going outside, at least. All right, so let's keep up to date with where we are in the class. So we are going to have a quiz number 3. So typical week here. Our quiz is going to be due this week. I think this is the wrong date. So this Friday at midnight. And then you may have noticed I pushed the homework back to be due on Sunday night. And that was mainly because apparently the file still wasn't accessible, and I didn't realize that until Sunday. So I took 2 days off of the potential time, even though I'm not sure how y'all checked, but I know a couple of you guys did. So I just gave you those 2 extra days back. So it's no longer due on Friday. Just check Canvas for that. As a reminder for homework as well, I'm not grading based off of correctness. That being said, though, I'm grading based off of effort, and I'm grading based off of professionalism and presentation. So please ensure that your writing and your presentation of answers and your methodology is very clearly stated. If it's typed, awesome. If it's digitally, so you can erase it and do that kind of stuff, awesome. Please do not submit a scrap paper written in pen with a bunch of stuff scribbled out. I will take off points off for that when it comes to formatting. So the goal of the homeworks is I don't expect you guys to know, or you're learning through the homework, so the homework is not a test. So if you're not sure, write out and make, formula, or write it out and show me your thinking, show the effort in there. Don't just put a question mark and submit it. I'm not graded correctly off of that, but just know that I want you guys to learn through these homeworks. So don't get stressed out and don't get anxious, and don't just copy your friend's paper just to submit a correct full homework. That's not the goal of these. All right, the other only thing I have this week, which I was hoping to get a nice pretty flyer because they're everywhere, but I couldn't find the digital thing here. But if you've ridden in an elevator, you've probably seen this thing. ETM, England, Timms and Miller, which is a major supporter of our university and also a really good development firm, land development firm here in Jacksonville. They're hosting a networking night. This is going to be next Tuesday from 4 to 7 p.m. over in the University Center down there. So they're always looking for internships. They have a really good intern program. They have a really good onboarding program. So if you're interested in environmental, or even you just want to meet some of the land developers in Jacksonville, then please feel free to come to this. I don't know if you need to register or RSVP. There's more information on that little flyer. Just go ride an elevator and see the QR code and all that stuff. Whenever they do send me the flyer, I will share that to the class in Canvas so you can get more information on that. But at least want to put this on your radar here for now. All right, the only other thing I want to go over here, just the one thing from quiz 2, just to go over this problem on here. We kind of touched on this at the very end of the class last semester, right before the weekend. So it may have just gone in one ear, not the other. But how you solve this is a very easy equation that's very important in geotechnical engineering. So again, these numbers might look different to you, but the general format of the equation would be one of the ones from our quiz. Sorry, I went the wrong way. So anytime you see some of these with void ratio, saturation, remember our good buddy George Washington. He may or may not be a soil engineer. But the equation that we're looking for is this one here. GS times W is equal to S times E. So the void ratio times the degree of saturation is equal to the moisture content times the specific gravity of our solid. Again, George Washington equals a soils engineer. Sewage, if you look at backwards, whatever way you can remember this, I highly recommend trying to just like plant this in your brain. So when it comes FE, when it comes to our exam time, when it comes to just talking to a geotech in general, like if you're at a networking event, you just say, hey, how about that sewage equation? And all the geotechs will be like, yeah. So if you're trying to win jobs or network that way, whatever, just remember this equation. So in this case, the things to remember, the things I see the most mistakes on is the way we present our moisture content or degree of saturation. So it's hard because all of these values are technically unitless, right? But think of the percentage as a unit here. So we can either do the moisture content and the degree of saturation both in percentage, or the degree of saturation and the moisture content both in decimal. But we can't show them, we can't have them like 1 decimal, 1 percentage. So in this case, like moisture content is 15%, degree of saturation 100%. So these cancel out, the percentages cancel out. So just keep that in mind. Like sometimes they might be sneaky and they might say like, okay, it's actually S is equal to 0.8. So if the moisture content is 15%, then you have to put S equals 80% in your little equation. You know, those percentages need to cancel out. So aside from that, it's just changing around here, the degree of saturation or this void ratio E, then, and you get a void ratio of 0.4. And again, double check your quiz solution, the methodology of this here. But this is the importance of this equation, and as well as remembering the units for this ER2. So one of the benefits of this that I talked about last class too is like we did this moisture content. We hopefully are all familiar how to find this now, right? Take a soil, put it in the oven, go to sleep, come back and take it out of the oven, and boom, you can get the moisture content. And then lab number 2 will be this one. And although it takes a little bit more time or a little bit more equipment for the specific gravity, it's an easy experiment to do. It's an easy value to determine. So this equation is really helpful because of that low-hanging fruit. We have these 2 experiments that are easy to do. You can knock it out in a day or so, and you can get a lot of information from this. The other thing that I said is often assumed here is this degree of saturation. That is, if it's equal to 100%, from below groundwater table. So this is also an assumption. At water or soil that is underneath the groundwater table, we are going to be assuming that it's been underwater for a while, or it's had enough time, geologic time, to remove all the air voids in it. Now this is a little tricky one because like if you take soil sample from underneath the groundwater table and you go leave it in the bed of your truck in May for 2 weeks, like it's not 100% saturated anymore. So like think of that still like when you are like dealing with soil samples here. Like yes, we can assume this if we are still diligent and careful with collecting our soil samples. So each week I try to just cover one of the quiz questions that are like a little bit lower, but as always too, like let me know if you want to go in more detail or like come to office hours. I'd be happy to go through the quiz questions each week. And hopefully again, I mean, you guys are adults now, so you understand this, but use these quiz, like to be sincere with them. Don't just like copy your answers. I know these easy to find. I know this stuff is probably out there, but like really be sincere and like use this as a metric to check your learning through each week. Okay, so we're gonna wrap up what we talked about last class. Again, I'm just gonna put these here, but hopefully you've already filled this out. I don't know why that deleted it here. But we started talking about this range of void ratios here. You have a question?
Yes.
So
you were just saying about how like different soils, like after time, you may not have like the same amount of filtration and stuff. When you take that core sample, like that, is that really just see the different layers of sediment, actually how dense the material is, or?
yeah, so it depends on the type of coring that you have, but yeah, there's different testing methods or different ways of retrieving soil out of the ground that will either keep the soil intact fabric wise, like to make it actually like a nice like representative of what it's like underground, or just pull it up just so you can run like a grain size distribution or something where the moisture, or one of these values that isn't going to change with disturbance, like compaction or void ratio. Yeah, we'll get into that whenever we start talking about the subsurface testing techniques. But your typical boring would not, like it will, you wash it with water to drill through it. So you're messing up the groundwater regime, you're messing up the soil fabric because you're essentially pressure washing the soil. So yeah, that's a good question. We'll cover that in a lot more detail in a few lectures. So what we were talking about was the importance of void ratio. Not only the in situ void ratio, but also this range of void ratio that soil can have. And this is all based strictly on the grain size distribution or the angularity of the particles. And we kind of talked about this last time, but like imagine having a bucket full of ping pong balls that are perfectly circular, or a bucket full of bricks or blocks that are the same diameter as a ping pong ball, but like stacking up within each other in a bucket. Like the ping pong balls are going to have a lot more void space and an essential higher void ratio than the blocks would have. So the angularity or the roundness of our soil plays a role, as well as the size distribution or the grain size distribution. Like if we have them all the same size versus a bunch of different sizes so they can fill the void space in between that the larger particles make. So this E max, E min, this range is really just the range of potential compaction. So our E max is in our loosest state, and our E min is in our densest state. So it's essentially saying like, okay, we have this type of soil. What is the range that we should expect to find it in the field? But also, what are the ranges of density that we can control it as well? Like if you're buying it for a fill for a project, either like a roadway project or an embankment project or something, you want to be able to control it with a set density and a set void ratio so we can get the strength and we can get the weight that we need. So that range is important. We talked about the different correlations to that. And what I wanted to like introduce is this theory here of what we call empirical relationships, which maybe some classes that you've gone over have used these before, but they are really, really heavy in geotechnical engineering, and that's because geotechnical engineering is very site-based. So empirical relationships take data from the field, from experiments, and then set some type of statistical correlation or statistical function so we can make a prediction based off of the data that we have. So this is really helpful, but there's a huge caveat we have to consider here is this function or this empirical equation is only accurate or is only proven to be like worthy of use for the data that is training it, essentially. The data is like using it. And this is a whole thing too with AI, if you've ever gotten into that, like the data that you're used to training your AI model is just as like one of the most important things. So this empirical relationship is only developed based off of these like factors here, this data that they use. So nowadays that we're sharing a lot more data and we have communications and we have collaborators and like in all the different continents and being able to share data, then we can kind of start to make some of these empirical relationships a little bit more robust or a little bit more applicable to various types of data. But it's always important to keep that in mind when you start seeing this. Because the geotechnical engineer is full of these empirical relationships. Hopefully you can start to identify them based off of these like equation formats. You know, they're usually pretty easy, pretty like linear or a log-based equation. Yeah.
It's the D50 and then the millimeters in parentheses, where do they both?
Yeah. D50. So this is a result, or that's a parameter, a result of the grain size distribution. I don't know how to spell. You guys did the grain size distribution in CE materials, and we will do it in this class as well if you haven't taken CE materials. That is the percent passing, or the diameter as a result of 50% of our passing of our sample. The millimeters is just saying that this function, this statistic, is set up assuming that number is in millimeters. So I will talk about that in a little bit. And again, the equation isn't as important. Like you're not going to like be using, like I don't expect you to know this equation. This is just one of the many empirical relationships that are out there. But this is a result or a parameter of the grain size distribution or the Steve analysis.
If you guys get any like error values when creating this graph, you guys just consider those, like for instance, if you guys get the clean sands, if that's like all the way at like 0.8, right? And do you guys just consider that negligible and take it out when you guys use it, or do you guys consider it still?
That's a really good thing. On here, so there's two different ways you can do it. You can have the confidence intervals, which are shown here. So those little dashed lines. So you're saying the data fits in here. And sometimes you might see these empirical relationships have like a plus or minus, like as a confidence interval. Like use this one, this is like 90% confidence. If you don't need something as reliable, then you can use these outer band equations, a maximum and a minimum for like 70%. But a lot of times it's very dangerous to cut out data or trim data for like no reason, you know, like, so in this case, this data up here, we start seeing a trend change a little bit. So maybe instead of like just cutting this out and being like, okay, it was never a thing, they just say this equation is only applicable for a mean size between 0.1 and 10. So they'll set bounds in the equation, kind of like a piecewise function, if you remember that from like the elementary school days or whenever you learned that. So yeah, there's a whole bunch of ethics that goes into empirical relationships and data fitting.
I'm guessing you just mentioned in your report that there was like that this one particular sample just went above our like safety lines.
Yep. Yeah. Okay. Yeah, and maybe there's a reason for it. Like maybe it's just an anomaly in your testing or something. You know, you can track that data back to be like, oh yeah, it was, you know, the Tuesday after the national championship and the lab techs in Ohio State fan. So he probably came super tired and messed up that time, you know. So like keeping track of like all of the intricacies of your lab testing, your data collection is important because you might have to look back and justify it in that way. Yeah, so empirical relationships, this is something you'll see a lot. The other version of this that you'll see too, that kind of the opposite, like ditch on the other side of the road, is an analytical or a theoretical equation. And this is more so based off of like physics or some law of science that's based off of. So it's not necessarily an empirical relationship. It's not trained off of data, but it's derived using like physics or mathematics. All right, so that's where we ended on lecture 5, but we had from Thursday, but we have a few more slides I want to go over. During the very beginning, when we were talking about a bunch of different types of parameters that we care about, I had mentioned submerged density. Submerged density is shown with a little apostrophe after it. And also more so what we use is a submerged unit weight, which is the gamma prime here. The other way of showing this to you might be gamma sub. And what we do is we use this when the soil is 100% saturated. And when the in situ soil is under the groundwater table. So submerged density and the effective density is also what it's called. It can be kind of hard to think like physically like what it means. The best way I was like kind of explaining is like, okay, you have a bucket full of soil and then you fill up that bucket filled with water. So the soil or the bucket now is a saturated density. But then let's say you take that bucket and put it underwater, like the perceived weight or the perceived density from your standpoint, since you're underwater too, is going to be lighter or it's going to be less dense, right? Because when you lift up stuff underwater, there's this buoyant associated with it. So that's kind of where this comes from a physics standpoint here. Like we have this density of solid and we have a buoyant force and we also have the weight of solid underneath it. The reason why we would use this is going to be highlighted, especially like the last month of the semester. So it's kind of hard, like we're going to fast forward essentially. But the whole reason why we would use this submerged density in our stress calculations or why it's an important parameter is because the groundwater table can potentially change. So long story short with this, we know that density is correlated to the strength of our soil. Remember I showed that little graph, density versus strength. It's correlated right there. So density is controlled by the soil weight, which is then controlled by the soil stress. So kind of what we were saying before, the frictional behavior of soil, the more so we're pushing down on the soil, the harder it is to like have those soil particles slide around each other. So density, if we are in a saturated condition, we see that the density of our soil is higher than if we were in a non-saturated condition, right? We know that gamma sat is greater than our gamma normal, which is greater than our gamma, dry. So the whole reason why we would use this submerged density is to account for the fact that maybe 20 years from now, or maybe even just a year from now, our project, that groundwater table might change and might leave. And so our calculations are going to remove the weight of water just in case that water is no longer there. So that's the whole essence of this. It's used to calculate something called effective stress, which we'll talk about like way later on, but it's used in this calculation of effective stress. And effective stress is just a way of saying we are not trusting the groundwater. We're not trusting the water in our site condition. So we're only going to look at the soil fabric. So in order for us to not trust that water, we are not going to include it in our strength design, which means we're going to remove it from our density. So that's why we get a submerged density here. So an example of this, and we'll highlight this too a lot later. Why would we care about this? The groundwater will change. So therefore the soil and the density strength, or the soil density and the strengths can change. And this is mainly so when we start talking about design or using earth or soil to achieve some type of structural purpose. So like for an example, like if let's say we have a retaining wall right here. So we know a retaining wall just from physics, why would this retaining wall want to hold up? Or like, how is it holding up?
Right there, gravity.
Yeah, it's just a super heavy thing, right? It's coming in and out of the paper. So like it might be curved to a little bit, but we know that there's a dead weight of soil wanting to push it that way because soil is granule, right? But then we also have this resisting force that's due to the weight of our wall. Now, in order to combat this, what a lot of times we'll see is a cantilever style wall. So this is a type of retaining wall where it would be an L shape. It might also go a little bit this direction as the other way. But now essentially the reason why we have this now is this block of soil is essentially causing it to stay in place. It's increasing the effective weight of our wall. So now this block of soil is allowing some resistance against this.
That what those traps do in the MSU wall?
Kind of. One spoiler. No, not really, but we'll get into that in a little bit. So essentially now we have something like this here. So we have a greater ability or greater resisting force on this. But let's say the weight of soil here is just this gamma value. So we can kind of assume that the more dense this soil is, then the greater the resistance force, or that greater that green arrow, right? The higher that density is, the higher that unit weight is, then the greater resistance we have on this. So let's say like we have groundwater table or some type of ponding or it rains and we have like water buildup in this area. So if we have this, then the groundwater table is now going to be our submerged density, and the weight is going to be therefore reduced effectively. So because of this, our arrow, our resistance down here is a lot smaller. So if we designed for this case where the density was wet and we have this case, then we could have failure because now this resistance is a lot lower. So that's why you'll usually always see weep holes or some ways so to ensure that water does not build up beneath that or behind the retaining wall, because you can change, or if you don't have that case, then you would design for the effective condition, accounting for the lower density of our soil. That's just a little example of that. Some of the ranges of these here, and again, this is equal to gamma sub. I just wanted to put that apostrophe right there just to get you guys used to seeing that. So gamma submerged. You can see the ranges of those and the different ranges of soils as well. And I know most of you guys are going to be used to PCFs, like pounds per cubic foot. Let's put this here. But I think it's always good to at least know a range of what is acceptable for the other units there. Let's say you end up working on like some international projects or something and they send you a report with this. It's good to at least be able to call before you put it in Google to transfer it over. At least good to know the range of it. Remember that the unit weight of water is 9.8 kilonewtons per cubic meter. So that's like the low end of it. So it should be in the teens to the low 20s per kilonewtons per cubic meter. So these are some of the general ranges. You don't need to memorize these ranges, but at least try to understand the general trends of them. Hopefully it makes sense based off of what you know of the composition of our material. Peat's an organic material. That's going to be a very light mineral or no mineral at all and just be plant matter or decomposing stuff. Obviously crushed rock, glacier tills, and gravels. These are larger, more dense materials, less voids. And then silts and clays are going to be a little bit like more void, more airspace, smaller minerals made up our soil, so the density might be a little bit lower. Okay, so the last one that I want to talk to was again just recapping what we know so far, some of these really important equations. The first one being the one I already talked about ad nauseum, but is very important. However way you remember it, please try to remember this equation. The other really helpful one too is the correlation for dry unit weight to moist unit weight. So our dry unit weight is equal to our moist unit weight or unit weight with some moisture or some water in it, if you don't want to use the word moist. divided by 1 plus that moisture content. And the moisture content is in decimal form. So it wouldn't be 1 divided by 100 and something. You could divide it by 1 plus or 1 point something. So you could rearrange this to solve for this way too. The other one too that is helpful with along the gamma dry front is specific gravity of solid times unit weight of water over 1 plus our void ratio. So it looks very similar to the other one, but a different parameters. And let's say we wanted to combine these two equations. So we could also solve for this. If the normal unit weight, 1 plus our moisture content times specific gravity times the unit weight of water divided by 1 plus our moisture or our void ratio. This is also a helpful equation. And then the other one that is important is the saturated unit weight. GS plus E divided by all over 1 plus E. So I went over the derivations of these. I would recommend at least memorizing this one. These aren't like critical to memorize. Because at the end of the day, if you have your void ratio, or sorry, if you have your phase diagram filled out, you can easily find these individually. But these are just more so like using your notes, like, so it'll help like for quick calculations in the field or when you start working as well. They're all related to each other through that phase diagram. So the things to remember with these though, always check or write your units down. This will be the best way to ensure you aren't messing stuff up, especially when it comes to densities. So I would recommend writing it in your equation and then physically like canceling them out to ensure that, you know, if your void ratios are in the same like decimal form, your unit weight of water, you're using the correct one, and your solution is in the correct format. Especially the unit weight of water, you know, making sure you're either using 9.8 kilonewtons per cubic meter or 62.4 pounds per cubic foot. I see that mixed up all the time there. The other thing too is remember that void ratio is in decimal form. So sometimes like you'll see an E value being 1 point or even 2 point something. It's supposed to be in that form, so do not transfer that over, like divide it to this percentage form, think it's in that. And also remember that moisture content is calced. Is calculated in decimal form for these equations. So when we do have moisture content in these equations, always divide it by 100, even though it's not shown in the equation. And we need to put it in decimal form for that. Okay, so that wrapped up lecture 5. So now when we start talking about lecture 6, we're going to talk more about the grain size distribution and what distinguishes the different types of material. So have you guys heard the word clay before?
Yes.
And silt? These are all like household words that we've probably all used before. And maybe you know some of the differences from a composition standpoint, but we're also going to see how that composition changes the physical behavior of our clay. And then we talk, or the difference between clay and silt or gravel. So this is all that, like, upon this thing called composition, or essentially like what is the parts that make up this whole entity. Because as we said before, you take a sample of soil, it's going to be made up of a bunch of different stuff. So in general, what we have are these 4 categories of particles based off of the size in geotechnical engineering. Because when we're talking about geotechnical engineering, we're talking about like soil mainly. So stuff that you can scoop up in a shovel. So we'll have clay size, silt size, sand size, and gravel size. What this is showing here, this is in millimeters, but this is the general range of our size of our particle. Now, this kind of helps see a little bit too, as how we can see the particles itself. For clay and for silt, you're going to need some type of tool. You're going to need either electron microscope or a microscope. And then obviously for sand, you know, everyone, if you eat carrots, you can see it pretty well, like you can see the sand. And then gravel particles will be much larger here too. Now, these next 8 sections here, this is the big differentiation between clay and sand. And this is why, like, us as geotechnical engineers, if we have a site with clay, we would attack it completely differently. We would design it completely differently than if we had a site filled with sand. And this is also why determining the percentage of each is important. So in general, the shape of clay particles, when you think of clay particles, I want you to think of like just plates stacked on top of each other. Now, these are like microscopic plates, and I'll show pictures of these here in a little bit. But the way clay forms is a long-term mineralogy of these sedimentations like stacking on top of each other. For sand, obviously, it's going to be like more spherical or granular. Now, some of the minerals that are composed in clay are some of like the crazy words that you've ever seen. It's called like smectite, montmorillonite, bentonite, illite, kaolinite. You guys may have heard of like bentonite before. Bentonite is used a lot in drilling. Like if you've ever worked in construction industry or any type of subsurface drilling, they would use bentonite as like a material to displace water, since it's actually denser than water. It's just a clay mixed up into it. So you may have heard that term before. But notice these are all ites, montmorillonite, smectite. I'm not a chemistry major and I don't really remember much, but I think that means it's like a crystal, it's a certain type of base, like crystalline structure. Where when we talk about the minerals composing sand and gravel, it's some of the stuff we've heard before, like you know, our salts, our quartz, feldspars, mica, some of the stuff that is more like day-to-day, you know, your geology class, you probably worked with graphites and that stuff. Now, for the forces involved, this is really important. Sand and gravel, this is all controlled by gravity because they're larger and they have enough mass. But for our clay-sized particles, they are so small that they are controlled not by gravity because they don't have enough mass, but rather they're controlled by electrostatic or van der Waals forces or endomolecular gravity. So much smaller design. And this is why when we start talking about like strength, the strength in silt, sand, and gravel, this is all from friction. And for clay, this is all what we call cohesion. You guys remember cohesion, that word? What is cohesion? Yeah, this. Particles sticking to each other. What's adhesion? Like something sticking to something else, but it's not the same thing, you know? But cohesion, these are the same particles that are attracted or repelling to each other. So when we talk about the strength of clay, we're always talking about cohesion. When we're talking about the strength of friction or of sand, we're always talking about friction. You might notice this like little dashed line right here, and that's silt. So silt is just like the awkward stepchild in between all of it. Like sometimes it can behave more like clay, and sometimes it can behave more like sand. So silt is a spherical-like particle that is just super, super, super small. And this is why, like, if you were to ask anybody, like, what is the most problematic soil type? I mean, aside from organics, like, they're going to be mainly saying like silt. Like, silt is just like the most like problematic type because it's neither friction or cohesive, it's somewhere in between. When we start talking about soil classification and that the tests associated with that, and especially when we start like working with some real soil, you'll hopefully be able to see like how silts are just, they're not fun to work with. So that's why we have that dash line there. We'll talk a little bit more like that. So some of the characteristics of this, again, with the clays, I've used this word already, but with clay, we call this cohesive sediment or cohesive soil. And just go back to red just to keep it consistent. So for sand and gravels on the other side, this is going to be cohesionless. We'll say cohesionless soils or cohesive soils. Now, silts are for the most part cohesionless. But I'm going to put a little asterisk there because it depends where you are. In Florida, we actually have a good amount of cohesive silts. But in some areas up in like the Pacific Northwest, there's a type of soil called a diatomaceous soil. Anybody remember from like biology class something called like diatoms? Like the little like bugs or something that like float around in water, or like plankton stuff. It's essentially a soil that's made out of the exoskeleton of that stuff. So it's like very, very hard to characterize. And it's not cohesive at all because it's a bunch of like little tiny dead like skeletons of things that look really, really cool under a microscope, but it's a pain to try to build a bridge on or a structure or anything like that. Like this is the general trend. The other thing that we would call clays from a characteristic standpoint is plastic. And I don't mean like plastic like as in rubber. I mean this from our strength of materials class and from a loading mechanics. So who remembers what that like plastic behavior means when it comes to like loading and then specifically unloading a material?
I remember the crowd, but when you unload it, it doesn't take the original shape.
Yeah, permanent deformation. So plastic, think Play-Doh. Like you have a shape of Play-Doh, you smush it, you remove the load, and it stays, you know, it doesn't bounce back to the normal spot of it. So plastic, clays are generally plastic, which means there's permanent deformation. But what we'll see also is there's still a little bit of rebound. So it could be like a steel that is being loaded past the yielding point. You know, if you load it, if you stretch a steel fiber out past the loading point, it's going to snap back a little bit, but there's still going to be permanent deformation. So we see for clay, it's very similar like that. Just going to go over to the other side, sands and gravel, generally non-plastic, meaning that the deformation will be recovered until it fails because it's frictional. So you're going to push it, and then it could recover, it'll bounce back, or you're going to push it, and it's just going to completely shear, and it's going to fail. So we would call like sands and gravels non-plastic. The other side of that is because it is frictional. So that's a characteristic of sand and gravel. Silts are also non-plastic. So they have a little bit more of the sands and gravel characteristic. But I'm going to put like frictional-ish. It's really hard to determine whether sand or silts will fail using friction or not, or how much they control by that.
So do we just normally not even consider building in silt?
No, you still have to, like most of the time, like you can't really, you don't have a benefit to it. It's just the amount of analysis is going to be a little bit more like in depth, you know, like literally, like you're going to have to remove, you're going to actually have to test, you're going to have to instrument the site. And that might be a barrier for some people, for some clients or for some owners. But most of the time, you know, like there's some areas where there's just silts, like all of like the Mississippi Delta, like a lot of that is filled with silts. And you're just like, well, gotta build there, so still have to make it work. So, okay, so the effect on engineering, on water, on the engineering behavior, and this is a very simple thing, but I want us to think like, again, physically, what happens if a water molecule comes in contact with a clay particle that is very small? Yeah, well, I mean, there's going to be a large effect. So all I'm putting here is there's a huge effect because of the similarity in size. Because water is a very similar size and it's electrostatic forces that control silt, the way silt sticks together. So think back, this is also why, remember that first video I showed of the quick clay conditions. Like that was the water, used to be salt water, had different electrostatic forces, and now it's fresh water. So now the soil is used to those electrostatic forces or whatever the salinity, I don't know, I'm not a chemist kind of thing. But since the water changed, the structure of our clay completely changed. So for sands and gravels, there's not really going to be like a change in it. Like not really, at least not for this class. Like you could get into how water affects different types of things. But the main thing that we talked about at the very beginning is that solid portion of our material is non-absorbent. So, you know, we can kind of discredit that out. Stilts. Yes, but not so much. So silts again is that little middle ground between there. So we'll see there's a lab experiment that we do specifically between clays and silts, or sorry, there's a lab experiment called the Atterberg limits test. And essentially what that test is doing is telling us how much the material changes properties by adding water to it. And one of the ways we can distinguish between clays and silts is through that test, because it'll tell us like if we add a lot of water to this material, the behavior changes pretty drastically. It's most likely a clay. This material is unknown. We're going to add a bunch of water. It doesn't seem to change that much behavior, so it's most likely a silt, even though it looks the same amount, like, you know, the same size, the same type of material. All right, so the effect of density on engineering behavior. This is where this side is huge. So compaction and like, you know, density of our sands and our gravel, this greatly affects the strength of our material. And why is that?
It uses gravity to push down.
Yeah, gravity pushes down, it's friction. I push on a little table and pulled the imaginary sandpaper out like a million times. So the more dense the material is, the higher the stress is, the harder it is to shear the soil. So the greater the density, then the greater the engineering behavior or the strength of our material. On this other side, our clays, not so much, because mainly they're controlled by cohesion. Mainly they're controlled by the electrostatic forces, like holding everything together. For silts, again, I don't know, kind of. It's awkward, you know, it's the middle ground. You're like, crap, it's going to be site specific. And if you want to make a lot of money in geotechnical contracting, then just go work for a firm that is really good at specializing in characterizing silts, because it's just one of those things that each case is different. The geologic condition, the location, the depth, the temperature, the mineralogy, all of that depends on the strength parameters. So that all needs to be defined. So one of the things we're going to start introducing here is the grain size, or the range of grain sizes. So this is where we start looking into the classification of soil, and we're not going to get into the classification until the next trimester or whatever you want to call it, after exam 1. But I at least want to share a little bit of this. So the Unified Soil Classification System, that's one of the languages that geotechnical engineers use to define soil. So this is one of the classification systems. Again, it's just like a language. Like you can communicate soil using other ways, other classification techniques, but this is just one of them. So they say that the gravel size particles is from 20 to 4.75 millimeters. Sand size particle is 4.75 to 0.075 millimeters. And our silt size particles is that range, then clay size particles is less than 0.02 millimeters. So since I have a computer, I can scale stuff. This is just drawn it to scale here. So if this gravel on a size particle is 20 millimeters, a lot bigger on this screen, but on my computer, if it's 20 millimeters, then a sand size particle would look like this. So, respectively, the average range, like we can still see the difference in it here. The silt size particle is going to be really, really small. And then the clay size particle, yeah, you can't even like see it in respect to the gravel. We're going to talk about this in the lab a little bit later, but this is an important thing to think about when we are talking about the engineering behavior. So if you have a bunch of particles this size, it's going to be a little bit easier to use like math and physics and all that stuff to define and see how it's going to like react whenever you apply a load to it. But if you have a bunch of stuff that size or that size, then it's going to completely be a different mechanic wise. Or let's say you have a bunch of this stuff covered by a bunch of that stuff. Does that silt help the friction? Does it hurt the friction? Does the clay help it stick together? Because remember, we're dealing with mixtures of this material. So the way I like to like kind of characterize it too, since a lot of us grew up in Florida and most people in Florida grew up with trampolines. If the gravel size is a trampoline, then the clay size particle would be a flea on that trampoline. So very, very small with respect to the gravel. Now, if you're not used to seeing these terms here, the micrometer, that's used a lot in this. Micro is just the inverse of a mega, so 1/1 instead of a million. And you also hear this term called a colloidal particle. That's something less than 0.001 millimeters. Now, there's not often times that we would care about colloidal particles because you're just getting into smaller stuff that doesn't really matter from a mechanic standpoint, but you might hear that term pop up too of what a colloidal is. So when it comes to the behavior of this, again, these are where the little pictures show up, are sand size particles, and again, stuff that you can see, stuff that you can characterize. But when we start getting into some of the silts, it starts looking the same angularity, but much, much smaller. And I should have posted a picture of the diatomaceous stuff. This is just a granule silt, so it looks very similar, just much smaller. But when we start looking at some of the clays, that's when the structure of it gets really crazy. So this is a adipolgite clay. It's a clay that's found in the Hawthorne group of soils. So it's here in Florida, and it can be very, very small. And that is going to greatly affect how it reacts to loading and greatly affects how it reacts to water. So just for reference, this little 5 micrometer screen is right there on that 50 micrometer screen, which is like probably the size of one of those clay particles. So it's hard to grasp that scale because to us, it's all just really small stuff, but really the size difference is pretty remarkable. And it can all be mixed together too, which is important to remember. So let's start with the easy stuff for coarse grain. So the behavior of this, it will behave according to their weight or their mass. So it's all gravitational force. So the density and packing is important for strength, which is why that void ratio is so important here. Now this picture is just a fancy thing, just showing how the forces kind of react through everything. And you can kind of if you want to get into modeling of sands and all this stuff called like discrete element modeling, which is like something crazy that computers can now do, where they model each grain of sand individually and they can see, okay, this grain of sand pushes on this, which pushes on this. It's like a giant reaction, and they can actually track that mathematically. So all that to say is that this coarse grain soils, I don't want to say it's easy, but it's maybe easier to model or predict the mechanics. Remember, the mechanics is just the ability to know when we load something, how is it going to respond, which is important for engineers. So it's math associated with loading and response. So in some cases, we can have the composition or the deposition play a role into this. Or also the compaction technique can play a role in this as well. And obviously it'll produce something like a dense material like we see here, where you're removing a lot of those air voids, a loose material. And then one of the interesting thing, like phenomenon in granule soils and in gravels and sands is we can actually have a honeycombing phenomenon. So yeah, I mean, I don't listen to Joe Rogan or like any of those people. I don't know if they talk about it, but like the honeycomb shape is just a weird thing that you see a lot in nature, you know, and even in like inorganic soil, a lot of times our geologic formations will have this kind of arching established in it. And essentially you see these little arches form. Now, in this case, we might have a very strong material in one direction, but it might be weak in the other direction. And so that's that fun word called like anisotropy or anisotropic, if you guys remember that word. You guys heard that word before? Yeah. Okay. Anisotropic just means the behavior or the parameters or the material is different in one direction than in the other direction. So you might see honeycombing in some certain type of geologic formations, and that's also why this comes back to the geologic composition and understanding what is expected in that area. So the grain size for coarse grain is nice and easy. As I said before, they behave according to their mass. So the things that we will care about is the void ratio and the density. But also these cannot alone characterize the anticipated engineering behavior. We also have to look at the structure and the angularity. This is why that deposition the geologic depositional process is important, or even the composition of it. So is like, this is just kind of like a cartoon example of how it could vary. So we have different, like if we have, remember, void ratio in the structure or the density. So void ratio is volume of void over volume of solid. And then our density is the mass divided by the volume. So let's just say each one of these like little bricks or one of these squares is a is like a volume, a unit volume or something. You can kind of see how like these might have a similar density, the same amount of mass in that little square, but the orientation could completely change the permeability, could completely change the strength, because this is more of a honeycombing versus a like well-graded material. And then likewise on the other side, maybe these different particle orientations, maybe they have the same void ratio. They have the same amount of volume of void and the same amount of volume of solid, but the way they are oriented could play a big role into behavior, right? Like this one might be really, really strong in this direction, but really weak in this direction. So again, the anisotropic behavior, where this one might be able to be loaded in all directions in the same way. So angularity and the structure still plays a large role into it, which again is why we need that geology insight on here. Because once we remove the soil from the ground, it's really hard to capture this unless we do some in situ testing or we test what the soil is like in the ground. But as soon as we put the drill rod in there and we pull it up to the surface and we throw the samples in the bed of the truck and we give the samples to the intern, all this is all completely messed up and we can't like reimagine it. Or we can't like reconstitute it. Okay, so let's look at clays now. These are some beautiful pictures of some of those different types of clays. So the behavior of clay is completely different. So completely different. It's controlled by the by the electrostatic forces, and hopefully you can kind of see why based off of this. The one on the right is a really cool one. That's a kaolinite. These are all scanning electron microscopes to image these. So you can't even image this with a optical microscope. Like you have to shoot electrons at it and bounce it off. Let's get it that way. But they're usually octagonal, again, kind of weird, like little like tiny crystals, depending on the parent group. And then they're always like stacked on top of each other like that. So this is why you have that like plate-like behavior. You know, you have like a group of plates stacked up and bouncing off of each other. So they're formed from gravel, sands, and silts. These are all usually formed from physical weathering, like abrasion. Abrasion. But clays are formed using or from chemical weathering. So that's like an example is like hydrolysis. So that's why the mechanics are completely different and they're more chemistry based. So the clays are much more sensitive to chemical changes, especially in the water, climate changes, and the geologic deposition. Like as I said before, was it deposited in salt water? Was it deposited in water and now is dry? Like that kind of thing. Like water has a bigger role in the grain size of clays. So for the three of you who like chemistry, these next two slides are for you guys. So clay minerals are composed of these super fun words that will impress all your friends back home. Silica, tetrahedra. Oh my goodness. What was that? See. PowerPoint was so impressed it messed up. So tetrahedron. And then alumina octahedron. So most of our clay minerals are composed of these two things. So silicon, hydroxyl, or aluminum. So something like that. And these are why they combine to form these different plates that then these plates are stacked on top of each other. So you would either get a silica sheet or an octahedral sheet. So this is what is actually making up these plates, is these two things. And hopefully you can see just based off of how this looks with triangles versus something that's a little bit more intact, how if you introduce other chemicals or even just the structure of that might change based off of like the orientation of it, you know, a slip surface right here where that might be a little bit more dense. So once we have these different types of sheets, then how they are attached together also plays a role into the mineralogy. So this is kind of like a cartoon that shows some of the three most widely types of clays and some of the words that we talked about before, like kaolinite, which is a silica sheet, and then a gibbsite sheet. I have no idea what that is, but it's 7.2, what is that, atomic units, which is really, really small. So just for example, 1 millimeter is equal to, just trying to memorize this off the top of my head. So yeah, I think that's it. I might be off. No, I wrote that down. Obviously, you don't need to memorize that, but just know it's very, very small. That's 1 millimeter. And this is only 7.2 of those astronomical units or atomic units. So kaolinite is one of the most common types there, and it's a very basic mineralogy. One of my personal favorite for somebody who grew up in the 90s, just used the word ill a lot. Illite is a good one. And that's connected with potassium and it has a little bit more structure, right? And then the other one that we talked about here, that's a mouthful, Montmorillonite. Montmorillonite. Now, all of these are just big words for right now. But what I want you to look at is how these are established or how they are set up. And then some of the potential issues that, or like how that affects the behavior if site conditions change. Like for example, Montmorillonite, since there is a water layer in between these with exchangeable cations, Montmorillonite is known as a expansive clay, meaning if water is introduced to it, it's going to expand because there's this buffer already built into the structure. So kaolinite is a very basic non-reactive material where, yes, it's small, but it's very basic. So if you introduce other minerals or other chemicals to it, it won't be very reactive. The illite could potentially change based off of the potassium, and if you add something to it in the water or in the soil that is reactive with potassium. But also illite is a little bit better structured because of those silica sheets on top of each other. Those kind of buffer that. Again, it doesn't matter like exactly all these fancy words, but in the industry, when you hear Montmorillonite clays, you usually think about a swelling clay, or kaolinite clay, you think of like a very like easy, like basic like type of mineralogy. And then illite, you think of something that could potentially be reactive. So if you're in that industry at all, you'll hear these words a lot. And what I talk about there is like because of this, the clay particles will carry a net negative charge on their surface, which means they will greatly affect the water because water is dipolar. So water and clay so this little cartoon is just saying, this is the clay particle, we're zooming in, we're seeing the water being applied to this because of the exchange of cations and the exchange of like the polarity of it. So why this matters in this case, it is often assumed once clay is saturated, it stays saturated. So once the degree of saturation of clay is 100%, so if it was once deposited in an ocean and the degree of saturation is 100%, like because of the attraction of that, even if that clay, if the groundwater table decreases, as long as it's not placed in an oven or like been like left outside at the surface and desiccated or something, then usually we assume that degree of saturation of clay is 100%, which makes the math and mechanics a lot easier. Yeah.
What does it say next to water and clay?
Oh, attract.
Attract.
Add rate. No, attract. Okay, 2 more slides here. So the whole thing is, again, like thinking like, yes, we are talking about clay particles, but also we're talking about like particles being combined with other things too. So the clay particles, like I'm sure everyone wants to impress their friends or with that trick at McDonald's. But you know, that's essentially what clay is doing whenever we are adding water or changing the water. So for clays and some silts, it is all electrostatic forces. All right, I don't know why that happens. So therefore the chemistry and the pore fluid is important or is critical. Especially when we think about like this clay being mixed in to some of the other materials. So if we have sand mixed with clay or silts mixed with clay, and we add water, then that clay can push up and cause some of the clay particles, or sorry, some of the silt or some of the gravel particles to move around. So clays can either swell or shrink with water. So we can actually have like swelling clays in Texas, Louisiana. This is really common where you build all these houses on clay in the wintertime, and then whenever the rainy season comes, the houses all get pushed up because the clay actually swells and increases. But also what we can see is can change plasticity, or they can change the mechanics based on its moisture content. So that's the important thing to remember with clays, and that's why we have experiments just to characterize clay based off of how the increase or decrease of water changes its behavior. So this last slide kind of shows a little bit of this. One of the things that we can do with clay that is important, important parameter is clay sensitivity. And because this has kind of an example of that quick clay. So for example, this is a little cartoon if the clay was deposited in fresh water versus salt water. So a lot of times what we'll actually care about is this clay is the clay sensitivity, which is shown by A. I don't know why, just like to stuff. So what we do is we test the strength of the clay or the cohesion of the clay in its natural state. And then when we divide that by the strength when we remold it. Remolded means just like we put it in the form that it originally was in. So the way to think about this is like, all right, let's say you buy a fresh new thing of Play-Doh, right? And we all are getting the nostalgic smell of Play-Doh in our mind right now. So if we pull that out right away and then smush it, and we see how much it like takes to actually like smush that Play-Doh. And then we take that Play-Doh and we remold it back into the container and we fit it back into the container. And we do the same thing over again and we smush it again. The difference in that, or the percentage, the first time would be the natural state. The second time would be the remolded state. And that would tell us an insight into how the clay is deposited. Because once we mess up the fabric, will it retain its strength? This is a very common thing you might hear people say. Down here, these extra quick clays. You remember that was that Norwegian landslide that we were talking about, the extra quick clays. This is where it's very strong in its natural state, but as soon as it is remolded or as soon as it gets messed up, it loses all of its strength. And then we have those crazy landslides as a result of that. So this is one of those ways that we characterize clays. We'll talk about some of the others, and then also get into some of the stuff for our exam in our next class. So that is all I got. I will post these videos too. I forgot to include those in there. Kind of shows some good examples, some more information on the Norwegian quick clays and like why that happened, as well as like how the sand particles might change with different types of, or how the behavior of the sand will affect it.
I have that question.
Yeah.
Do you mind? We didn't